All right, in this video I'm going to talk about the geometric multiplicity of an eigenvalue, which is a kind of simple operation, but it's basically going to make together and put together the things that we basically saw in the previous videos and so on. But it again is pretty simple. So in order to find the geometric multiplicity of an eigenvalue, that we're gonna go lambda. It's not that it's not me that call the eigenvalue lambda, but this is the most used letter for the eigenvalue, so I'm just gonna stick with the standard. So the geometric multiplicity of an eigenvalue is equal to the dimension of the matrix that we're going to call A minus the rank of the matrix. So our matrix with, again, I call A, minus lambda I. And by I mean the identity matrix. So let's just show you an example. So let's suppose that you had to find the eigenvalue of find the I'm sorry, I was just find the geometric multiplicity of the eigenvalue, I don't know, lambda equal 2 of the matrix I don't know, let's start with let's have a 3 by 3 matrix. Is gonna be fine. Yeah, I think it is. 4 2 0 negative 1 1 0 and 1 1 2, a 3 by 3 matrix. Okay, so the the geometric multiplicity of the eigenvalue lambda equal 2 of this 3 by 3 matrix. So lambda is equal to 2. What I'm going to do here, and of course our A is equal to this matrix here, 4 2 0 negative 1 1 0 1 1 2. A is the one that I use in the formula, so let's when I said let's call the matrix A, so this is our A and this is our lambda, the eigenvalue and the matrix. So the idea here is to get here, but in order to get here we have to, well, we already know the dimension of A is going to be 3 because it's a 3 by 3 matrix, so the dimension is, is pretty easy, it's 3. We have to subtract the rank not just of A but of A minus lambda I, where I is the identity matrix. So first thing first, A minus lambda I just find A minus lambda I. So we already know A, which is our matrix, 4 2 0 negative 1 1 0 1 1 2. Okay, minus 2, which is the eigenvalue, times the identity matrix. Now the identity matrix is basically 1 over the main diagonal and 0 all over the place. So a 2 by 2 matrix is going to be 1 0 0 1. In a 3 by 3 matrix is pretty much the same, but in 3 dimensions, so this is actually 1 0 0 0 1 0 0 0 1. So 4 by 4 matrix would be the same, but we all the 1 getting the main diagonal. So the identity matrix has some pretty useful properties. This is just one of these. So one of the ways used. So it's gonna give us, well, 420 negative 110 112. This is gonna stay the same, minus, and this is basically gonna become, you know, 2. But when you multiply those kind of matrices by a scalar, so a number, you're basically multiplying each and every member by that scalar, so that number. So basically gonna get 2 0 0 0 2 0 0 0 2, and then we're just gonna subtract this matrix with just these other matrix. So it's just gonna be, you know, normal subtraction, 4 minus 2 and so on. So it's really gonna be, you know, easy. Should I do that? Well, easy. Come on, it's pretty easy. 4 minus 2 is 2. 2 minus 0 is 2. 0 minus 0 is 0. Negative 1 minus 0 is negative 1. Negative 1 minus 2 is negative 1. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 0 is 1. 2 minus 2 is 0. So our matrix is 2, 2, 0, negative 1, negative 1, 0, 1, 1, 0. This is our new matrix, which is A minus lambda I. So, well, we're getting closer, at least. We now can find the rank of our newly found and created matrix. So we're just gonna find the rank of this matrix. So the rank of this matrix of 2, 2, 0, negative 1, negative 1, 0, 1, 1, 0. If you remember, we just wanna, you know, we just wanna have a pivot, a pivot, a pivot, and 0 here. So I'm just gonna start by exchanging the first one with the second one. Exchange the first one with the second one. So it's gonna become negative 1, negative 1, 0, 2, 2, 0, 1, 1, 0. And we can already see that they're linearly dependent. So I'm just gonna multiply the first one by negative 1. So this is gonna become, you know, 1, 1, 0, 2, 2, 0, 1, 1, 0. So we're kind of lucky. Then I'm just gonna do I'm gonna multiply the second one by 1 over 2. It's gonna give us, well, the first one is gonna stay the same, 1, 1, 0, 1, 1, 0, 1, 1, 0. Well, now we can just subtract them. So I'm basically gonna subtract them. So I'm gonna subtract, I'm gonna do, well, I just get rid of the third one. So the third one minus the second one. So 1, 1, 0, 1, 1, 0, 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 0 is 0. And then I'm gonna do the second one minus the first one. So 1, 1, 0, 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0, 0, 0. Alright, so this is our only pivot over here, because all the other rows are linearly dependent. So we have pivot, equal 1, row equal 1, column equal 1, and by row, once again, I mean linearly independent rows equal 1. By column, I mean once again linearly independent column equal 1, and therefore the rank is equal to 1. Okay, so we're pretty close to the final, because we found we had an eigenvalue, we had a matrix, we found the new matrix, we found the rank, we computed it, and we found the rank with the Gauss reduction and so on, and we Gauss Jordan reduction, we basically found the rank, and the rank is equal to 1 because they were linearly dependent. So with this in mind, we can say that the geometric multiplicity of lambda is equal to the dimension minus the rank. But the dimension of a 3 by 3 matrix is 3. So the geometric multiplicity of the eigenvalue of 2 is basically equal to the dimension, so 3, minus the rank that we just found, which is 1. So this gives us that the geometric multiplicity of 2 is equal to 2. And this is pretty much it.